Thank you for coming to my presentation today. Our topic is continuous evolution of Tianwu's Pangolin8RAT and custom Cobalt strike beacon. This talk deeply described the two types of malware observed in September 2025, which we assessed to be related to Tianwu, the China Nexus APT group initially reported in 2022. Their malware, including Pangolin8RAT and custom Cobalt strike beacon, had significant evolution this time, including binary obfuscation, the elimination of RTTI, and new detection evasion techniques. We will present these findings along with an indicators and detection rules to help blue teams identify Tianwu's malware and activity inside their network. Before getting into the content, let me quickly introduce myself. My name is Naoki Takayama, and I am a security researcher working at Internet Initiative Japan, also known as IIJ, the Japanese commercial ISP company. I am a member of IIJ sect, the private CSIRT of IIJ group, and during my daily job, I am responsible for threat research and also incident response. For threat research, I mainly focus on tactics and malware used in targeted attacks, specifically targeting countries in APAC region. And here's the agenda of today's presentation. First, I'm going to introduce some basic facts about Tianwu and the brief timeline of the events we have observed. Next, I will overview the malware analysis result of Pangolin8RAT and its loader. This includes the entire execution flow, file system artifacts, architecture, details of C2 communication, and evolution compared to previous samples. After that, I will also walk through the malware analysis result of Tianwu's unique custom Cobalt strike beacon. This time, we have successfully obtained both downloader and beacon payload of it, so we will showcase several findings from them. As a wrap-up, I will showcase several detection rules and IOCs, which is beneficial for Blue Team members to detect Tianwu's malware and related activities. So, Tianwu is a China Nexus APT group active since at least 2020. They are also called Operation Dragon Castling by Gen Digital Inc., and the group is known to target organizations in the online gaming and gambling industries, as well as transportation, telecom, and government sectors across the APAC region. Previous research predicted that their motivation might be cyber espionage, and also domestic surveillance of citizens in China. During their operations, Tianwu has deployed multiple malware families, including Ketsuya, Pangolin8RAT installer, Core X loader, Pangolin8RAT, and a custom Cobalt strike beacon. Tianwu is a name given by Team T5, and they have presented very interesting and also detailed research in 2022 at Black Hat Asia. Following that disclosure, no publicly reported activity associated with Tianwu was observed for several years, until the resurgence described in this research. In September 2025, we identified two malicious files uploaded to VirusTotal that loads Pangolin8RAT and the custom Cobalt strike beacon. Because both malware were previously attributed to Tianwu, we assessed that malware can be related to their attack campaign, potentially done within 2025. However, there is still a possibility that both Pangolin8RAT and custom Cobalt strike beacon have been shared to other threat groups, so accurate attribution was challenging this time. But we still have medium confidence that Tianwu is a relevant threat group because we identified multiple TTPs overlap and evolutionary extension from past Tianwu's operation. Anyway, both samples were submitted from Singapore by the same uploader, suggesting a potential operational linkage. This is a timeline of the events we have observed. We will mainly discuss about events colored in purple today, which is the events observed in 2025, but as we introduce later, we have also discovered malware samples observed in 2024, which is also highly possible to be related to Tianwu's activity. Anyway, I want to emphasize that after an apparent inactivity period of 2 to 3 years, Tianwu's activity appears to have resumed or observed again in 2024 and 2025. So here's the first section, in-depth analysis, core X-loader, and Pangolin8RAT. The execution flow of Pangolin8RAT observed in this campaign is illustrated in this figure. A legitimate executable, regsvr32.exe, is abused to load avast.svc.dll, which serves as a core X-loader payload also attributed to Tianwu. Notably, core X-loader verifies the file names of both itself and its module file before performing any malicious behavior. If the file names do not match the expected values, core X-loader terminates execution without performing any further actions. Upon successful validation, core X-loader reads its binary data embedded in its PE resource section and applies XOR decoding, followed by AES decryption, and executes the resulting payload as a shellcode. The shellcode functions as a reflective DLL loader that loads Pangolin8RAT on memory. Notably, core X-loader and Pangolin8RAT observed this time were both heavily obfuscated to obstruct malware analysis. Core X-loader decodes data stored in its resource section using a hard-coded 64-byte XOR key. In contrast, earlier samples embedded similar binary data in the resource section, but it was AES encrypted with the key derived from the victim's computer name. And this image shows the content of the XOR decoded data. We refer to this structure as an AES encrypted data blob, as it contains AES key, the initialization vector, and the encrypted shellcode, which is decrypted using the Windows Crypto API during runtime. The decrypted shellcode loads a DLL file embedded at the end of the shellcode. The original file name of the loaded DLL was lightcore-x64.dll, which matches the previously reported PDB file path, lightcore-x64.pdb, associated with Pangolin8RAT. Previous research mentioned that Tianwu had used toolkit named PE2 shellcode to convert Pangolin8RAT into a shellcode, according to the PDB file path present inside the shellcode. This time, we could not find any relevant PDB path in the decrypted shellcode, but we are still confident that Tianwu have used same techniques and toolkit from previous attack campaign. Pangolin8RAT is a modular rat known to be used by Tianwu APT group. As same as other modular rats, its functionality can be extended through plugins retrieved from a C2 server. Pangolin8RAT supports 9 communication protocols, including TCP, UDP, HTTP, HTTPS, and more. Notably, Pangolin8RAT accesses the Chinese file sharing service named NutStore, which is highly likely to be controlled or abused by attacker. Pangolin8RAT creates or reads multiple files under the certain working folder during runtime. The path of working folder is read from the file edrconfig.dat under the working folder with module file or C program data. If edrconfig.dat is not available, C program data nv started folder or nv started folder under the temporary folder will be used as working folder path. This isn't the only case, but Pangolin8RAT observed this time frequently uses keyword EDR, and also Avast for both temporary file name and internal strings. Tianwu may have tried to disguise Pangolin8RAT as security product to decrease the risk of being caught by security professionals. The architecture of Pangolin8RAT is illustrated in this figure. Upon receiving a command from an attacker, Pangolin8RAT downloads a plugin from the C2 server and saves it under the working folder with certain file names shown here. In addition to standard plugin, Pangolin8RAT handles a special plugin named Plugin Manager, which will be saved as xdr tickcount.log file. This plugin has a capability to load and manage other plugins dropped by Pangolin8RAT. Once the plugin manager is downloaded, Pangolin8RAT calls its export function named init_edr_svc to initialize and load plugin manager on memory. After then, plugin manager will load and process other plugins dropped by Pangolin8RAT, which will be saved as kb_tickcount.dat file. All plugins including plugin manager, which is saved under the working folder, are deleted when the infected system restarts. Compared to other modular rats like Shadowpad, Pangolin8RAT does not implement PE loader functionality, but it uses standard load library W API function instead to load plugin on memory. Because it writes a plugin on file system and also loads it using standard Windows API, this behavior is very characteristic and also easy to detect. These are the files that can be created during runtime or placed by the attacker under the working folder. As mentioned in prior slide, file xdr_tickcount.log is a plugin manager, and the file kb_tickcount.dat is a normal Pangolin8RAT plugin. File named nvstarted contains configuration data, and it will be read or created if not presented. File intelcphs.log and edrconfig.log will be both used in C2 communication. Pangolin8RAT samples from previous attack campaign also handles similar type of files, but all the file names and folder paths it references were updated in this sample. Although, there are many minor changes, including export function name of plugin, hard-coded credential, and runtime behavior. According to the implementation, Pangolin8RAT can also read and use relevant data from its PE resource section, but the sample observed this time did not use this mechanism except for configuration data. Anyway, because each file has a unique name, this is also a strong indicator to detect host infected with Pangolin8RAT. Some of the files will be mentioned in later part of this presentation, so please check it out. Pangolin8RAT attempts to connect WebDAV server of NotStore, a file sharing service operated by Shanghai Yijing Network Tech, the Chinese company. Previous Pangolin8RAT sample also connects to this WebDAV server, but there was a minor difference of the timing where it makes a connection. Also, this network resource is not directly used by Pangolin8RAT for command and control, but it may have been leveraged to deliver plugin or additional files during post-exploitation phase. Pangolin8RAT stores its configuration data in PE resource with ID 1825. There are fields like comment string, which might be used as campaign ID because it is sent to C2 server when initial communication occurs. In this case, string says Z comment here was present, so it might be just a placeholder. After that, protocol, address, and port number of C2 server is defined. In this case, HTTPS protocol, address fretter.org, and port number 443 were specified. When HTTPS protocol is used for C2 communication, An HTTP request, as shown on the figure here, is sent to the C2 server. Payload data will be stored in cookie request header using the structure described on the next page. The custom request header, xedr app ID, with value avast, is present in every request. The cookie data is organized into the structure shown here, then base64 encoded, and then sent to the C2 server. The response from the C2 server follows the same structure. As you can see, there are fields like payload size, command ID, and CRC32 hash. Also, actual payload will be compressed with LZNT1 algorithm using RTL compress buffer function and placed at offset 0x10 of the cookie data. This is a list of command ID that we have confirmed in this sample. All the IDs were reordered and also modified compared to previous samples, especially the first 6 hex digits, 0x202204, which may represent a malware version identifier because previous samples contain values such as 0x191817 and 0x202103. Interesting fact is that malware used by other Chinese APTs, such as PlugX and ShadowPad, manages similar value to identify plugin versions and so on. Developer of Pangolin8RAT might reference their source code, since there are also similarities in C2 communication protocols and so on. These are the command IDs sent from the C2 server to malware. Other than core functionality of modular rat, Pangolin8RAT also has a functionality to execute shellcode sent by the C2 server. This capability might be used to deploy additional malware or attacking tools on victim host. When Pangolin8RAT accesses the C2 server, it checks for the file intelcphs.log under the working folder. If the file exists, Pangolin8RAT sets the value of the host request header to the file's content. In addition to the information from malware analysis, we have also got findings from tests and live access against host fretter.org, which was configured as Pangolin8RAT C2 server this time, while it was up and alive. Concluding the information, we are highly confident that host fretter.org functions as a reverse proxy that forwards HTTP requests containing a specific host header to another server, which we assess to be the actual Pangolin8RAT C2 server, behind the reverse proxy. Possible layout of the attacker's infrastructure is shown in this diagram. So, only the victim with valid intelcphs.log file can access actual Pangolin8RAT C2 server, behind the reverse proxy fretter.org, which is a server controlled by Tianwu. Interestingly, we have confirmed that host fretter.org was running Telegram bot crawler service that collects and stores bunch of messages from Chinese Telegram group. This might be related to Tianwu's other operation targeting entities in China. From this point, I will introduce several evolutions observed in Pangolin8RAT this time. First one is a binary obfuscation, which was used in both the core Xloader and Pangolin8RAT. Almost all the predefined strings in the samples were heavily obfuscated using an XOR-based algorithm. Because address of Windows API functions were dynamically resolved using obfuscated strings, it also hardens to locate and track malware's feature within the binary. Several Pangolin8RAT samples deployed in earlier campaigns also employed string obfuscation, typically using a shared parameter across all strings within a sample. In contrast, the current sample obfuscates each string with a unique parameter, significantly increasing the effort required for automated deobfuscation. Next evolution is the suppression of RTTI, the runtime type information. The Pangolin8RAT sample observed in this campaign suppresses C++ RTTI, including class names and inheritance hierarchy metadata. As a result, identifying class instances and reconstructing high-level code structure becomes significantly more difficult, complicating static analysis and control flow understanding. For example, Pangolin8RAT implements C2 communication protocol within class that inherits class named connect session. Each classes have name like HTTPS connect session and SSH connect session, which helps to identify routines related to C2 communication. In the sample observed in this campaign, all those information was gone to obstruct the malware analysis. Last evolution is detection evasion mechanisms, specifically targeting some antivirus and EDR software. As mentioned earlier, Pangolin8RAT sample observed in this campaign reads or saves its configuration data to a file named nvstarted under the working folder. At this point, if a process associated with a security product from Sophos or Kaspersky is detected, the configuration file will be XOR encoded using the victim host's computer name as the key. We assume that these software might support detecting unusual behavior of Pangolin8RAT, or at least placeholder string or something present inside the configuration data. So Tianwu has decided to XOR encode it before writing on file system. That is all for findings from analyzing Pangolin8RAT, and in next section, I'm going to walk through the information regarding Tianwu's custom Cobalt strike beacon. The execution flow of custom Cobalt strike beacon observed in this campaign is illustrated in this figure. As shown in this figure, an unknown but possibly legitimate executable loads the malicious DLL file with original file name testload x64.dll. The DLL extracts an embedded binary blob, writes it to the disk, and XOR decodes the content and executes it as a shellcode. The shellcode acts as a Cobalt strike beacon stager, establishing communication with a C2 server and reflectively loading the custom Cobalt strike beacon payload on memory. Notably, as same as CoreX loader, shellcode loader used here checks if the module file name matches with setup.exe or dlhost.exe. And only when it matches, shellcode will be executed on memory. Interestingly, the Cobalt strike beacon stager payload observed here embedded the ACAR string, the string used to test antivirus software detection. This artifact suggests that Tianwu may have been using a trial or pirated version of Cobalt strike framework. However, an ACAR string was not present in the custom Cobalt strike beacon payload. This observation suggests that Tianwu customized and rebuilt the beacon payload itself while continuing to reuse a default stager payload. This time, we have successfully obtained and analyzed custom Cobalt strike beacon payload downloaded from the C2 server. Tianwu's uniquely customized beacon payload exhibits several differences compared to standard Cobalt strike beacon payload. First, it uses an embedded beacon object file for customized sleep mask implementation. Once beacon is executed, embedded beacon object file will be decoded and executed on memory. From the debug strings inside the binary, we assume that this beacon object file was developed based on code inside Cobalt strike Arsenal Kit, the official sample code base published by its developers. This beacon object file will mask in-memory code of beacon and also heap memory using a random 13-byte XOR key to evade memory-based detection. Next, we have confirmed that this beacon payload has modified encoding method for its configuration data. Configuration data is hard-coded inside beacon in XOR encoded state using 6-byte XOR key written here. In contrast, a standard beacon typically uses a single byte XOR key, like 0x2e and 0x69. So this is another big difference compared to standard Cobalt Strike beacon payload. Moreover, we have confirmed that structure and format of configuration data were same from the standard Cobalt Strike beacon. We have modified 1768.py, the Cobalt Strike beacon configuration data parser originally developed by Dider-Stevens, to decode configuration data from custom beacon payload. We have uploaded the full content of parsed configuration data on GitHub, so may check it later. Interestingly, license ID section says 0, which is another evidence that Tianwu is using trial or pirated version of Cobalt Strike framework as a code base of their toolset, including custom beacon payload. By the way, as you can see in this image, the C2 server's host was set to lbi7.com here. However, when we examine the HTTP post headers definition in the configuration data, we found another suspicious host, hyperchat.org there. There are multiple possibilities for this artifact, but we assume that this is a residual configuration from a previous attack campaign, possibly done or related to Tianwu. After some research, we found malicious file communicating with host hyperchat.org on VirusTotal. As shown here, it was a default Cobalt Strike beacon stager payload, and at the point of our analysis, this host was already down and C2 server was inaccessible. This Cobalt Strike beacon stager was dropped by certain executable, which is disguised as Adobe Flash Player installer and packed using VM Protect. It was uploaded to VirusTotal from Singapore on October 24th in 2024. Interestingly, compile timestamp and upload timestamp of the dropper only has a 2.5 hours difference. This suggests that Tianwu may have uploaded malware to VirusTotal by themselves to evaluate antivirus detection coverage. As mentioned earlier, Tianwu's malware observed in 2025 were also uploaded to VirusTotal from Singapore. We do not have confidence about operational linkage between samples observed in 2024 and 2025. But malware observed in 2025 also may be uploaded by attacker themselves as a last preparation task before the deployment and actual intrusion activity. Now, I will wrap up my presentation. Tianwu continues to rely on Pangolin8RAT and custom Cobalt Strike beacon payload as part of its operations. Pangolin8RAT has evolved significantly, incorporating stronger obfuscation and RTTI suppression and detection evasion mechanisms, which targets specific antivirus and also EDR software. Although Tianwu's activity was not publicly reported after March 2022, and available evidence suggests that the group resumed activity dating back to at least October 2024. These findings indicate that Tianwu likely to remains as an active threat, underscoring the need for continued monitoring and vigilance. We have uploaded several Yara and Sigma roles on GitHub repository, so Blue Team members can utilize them to detect Tianwu's malware and its activity. Especially for Pangolin8RAT and ColorX Loader and custom beacon payload. I hope it is useful for defenders from each organizations here. These are the JSAC2026 file hashes of malware observed this time. These are already on GitHub too, so if you want to search or research about it, please reference it. And also IOCs for its C2 servers. As you can see, both Pangolin8RAT C2 server and CoreX Beacon C2 server, Cobalt Strike Beacon C2 server has a different C2 servers, but they was present, and I guess Pangolin8RAT C2 server was already closed on the October 2025, but Cobalt Strike Beacon C2 server was already still active at the point of December 2025, so it may have been leveraged at the recent operations too. These are the related researches which were really helpful for me to attribute Tianwu and malware observed this time. I want to pay tribute to all the researchers involved in it. That is all for my presentation. Thank you for listening.